now. Okay, good.
Okay, so in this talk, I will talk about low-dimensional topology and geometry, and I will be comparing some invariants of 3 manifolds and 4 manifolds. I can now hear myself like an echo.
So you should mute mic from here.
So, may I continue?
Yes.
Okay. Yeah. So there is this very old story of comparing low-dimensional geometry and low-dimensional topology, which started many years ago. I don't even know when, but Milnor was one of the first people who proved many things about singularities of surfaces and their topological shadows. So I will start with a very easy example. So our goal is to study some geometric objects. So we study analytic singularities. So this means that we have a function which has some point where all the derivatives are zero. So there is some singularity. For example, if you take this equation x squared plus y cubed, x squared equals y cubed, we can draw this curve, and we see that there is this cusp point at zero where kind of the tangent line is double line, right? And so when we want to study this singularity, so we can study it by analytic or algebraic methods. So we can look at the local ring and study its invariants, or we can also try to ask what kind of like topology is there. Yeah. So for this we intersect. So this picture lives in C2 because we have two variables and it is over complex numbers. So if you want to know what happens around this point 0, 0, we intersect our curve, our complex curve by a three-dimensional real sphere, which is like points which are close to zero and in some radius. And what we obtain is something one-dimensional because the sphere has codimension 1 and the curve has codimension 2, and they intersect transversally. So it means that the result is codimension 3 in C4. So it is just one-dimensional object which lives inside this three sphere. And three sphere from the point of geometry is almost the same thing as R3, right? Because this is just R3 with a point in the infinity, at the infinity. So it means that we have a one-dimensional object in R3. And if we compute it, we will see that it is actually this nice trefoil knot. So it is some closed curve which is knotted like this, and it gives us this famous trefoil knot, which we can denote T23 because it is the first of the family of torus knots. So the knots which you can wrap around the solid torus. So so this is classical observation that you can get knots out of the singularities of complex curves. And for example, one way how to see that the curve is non-singular is when you get a knot there. Yeah. So sorry, when you so it's like actually I'm sorry because I hope so. I just got confused by myself. So this is an exercise, what happens around a non-singular point. Um, so in general, you cannot get very interesting knots. You can only get torus knots, and you can also kind of take the knot and take some part of it and replace it by another torus knot. So you can kind of put many torus knots together, but this is all you can get. And in particular, you can never get hyperbolic knots. So the knots which are interesting from the point of three-dimensional topology or like knot theory in general, knot theory, those are usually these hyperbolic knots, such that you can put a hyperbolic metric on the knot complement, and this you can never achieve by taking a singularity. So so now I want to state it in more generality and maybe a little bit more precise. So our data is a polynomial in complex variables x, y, z, etc. And it satisfies the condition that all the partial derivatives are zero at the point zero, so at the origin, and nowhere else near zero. So it means that there is just one point where this condition is satisfied, locally close to zero and zero. And then we say that F defines an isolated hypersurface singularity. So what that means is that on this picture, if we take, you don't see my cursor, right? But if you look at this red
We do see, we see your
okay, great. So you see this red singular curve or surface. It's hard to draw high dimensions, but this is the solution of f equals 0. So here I draw C, so this is a preimage of 0. And this, because of this condition on partial derivatives, there is one singular point on this hypersurface where the implicit function theorem fails. And so if you want to study this singularity, so one way what we can do is take this sphere around it and intersect it, so we get this topological information. This is this L, which is called link of the singularity. So in case of knots, it was just sorry, in case of curves, it was a knot inside S3. In general, for surfaces, for example, it will be a 3 manifold in S5, or you can get 7 manifold in S9 or whatever. And also there is another way how to study this singularity, and this is by so-called smoothing. So we consider a slightly different equation, f equals some small number t, and we intersect it with a very small sphere around 0. So this if it takes t very small, we should still get quite a lot of information about the singularity, even though that now it's non-singular. And if we take this little sphere, we make it compact with boundaries, so it doesn't go to the infinity. And we also kind of get rid of possible singularities somewhere else. Yeah, there could be like a singularity very far away, but we avoid it by taking very small ball. So this is an invention of Milnor, and it's called Milnor fiber. And what is nice about it? So first of all, it is a smooth manifold with boundary. So we can use the usual different geometry machinery. And second, it actually forms a nice vibration over these complex numbers without zero, because you can always identify the fibers which are close to each other, so you can get locally a trivial vibration. So this is a vibration of manifolds with boundary, and if you want to get some easier things to work with, you consider just the cohomology of each of these fiber. So this is now a vibration of vector spaces. And if you go around by a loop around 0, you will get a monodromy of this vibration. So this vibration is locally trivial, but of course there can be some non-trivial monodromy operations. So so linear operator matrix going from H of empty of this Milnor fiber back to H of empty. So this matrix is an important invariant of the singularity, and we can get many information about the singularity by computing the eigenvalues of this matrix. So this is the monodromy matrix. And last point is that this link of the singularity, which is intersection with a small sphere instead of a ball, is actually it doesn't matter if you take it for the singular surface or for the smooth surface, because those are homotopy equivalent. So the point is that kind of when you only take the sphere, then you avoid this singular point. So it doesn't really matter which of the surfaces you intersect. So if you only, so this is very important, and it also fails for singularities which are not isolated. So yeah, and I said that when I said that we want to study a topology of this singularity, so basically when we know this link L, we actually know everything about the topology, because this surface, this singular surface intersected with this little ball is just a cone over this link, which is a smooth closed manifold. Okay, are there any questions to these definitions, notions? Yeah, it is maybe very familiar for you, or at least it shouldn't be very complicated. Okay, so let's proceed. So yeah, so now I want to describe. So so this is my monodromy operation T. Now I want to describe some invariants in more detail. So there are basically two ways how to construct an invariant of a singularity. So one way is what I already described, that we take smoothing. So we take near B fiber, which is smooth, and we take the monodromy transformation around a singular value. The other way how to do it is more like analytic or algebraic. I mean, this is also analytic, because this is an analytic family, but we can take the resolution of the singularity. So this means that we find another surface or hypersurface x tilde, such that yeah, sorry, actually this is usually not a this is usually not given y1 function. So I will talk from now on, I will talk about surfaces. So x is a singular surface, and we take a resolution. So this is a non-singular surface such that it is isomorphic to x everywhere except from the fiber over the singular point. So over the singular point, you have say bunch of curves or bunch of hypersurfaces, but everywhere else it is an isomorphism. So this is another way how to get invariants. So some numerical invariants are, for example, this Milnor number mu. So this is just the dimension of this cohomology of Milnor fiber. And I didn't say other important theorem of Milnor, which says that this MT is actually homotopy equivalent to a bunch of spheres glued at a point. So actually this cohomology is non-zero only in the middle degree. So and it is a free Z module. It is a copy of Z's for each of these spheres. So if we take the number of the spheres, we get the Milnor number. Then we have the signature of MT. So MT is a closed form manifold. Sorry, it's an open form manifold. But on every for manifold, we have the intersection form on the second cohomology, so we can take the signature of this lattice. Another invariant is geometric genus, which is H1 of the structure sheaf on the resolution. So this is a sheaf cohomology on the resolution. And what is interesting is that these three invariants are actually related. So even though that this one is defined by quite a different procedure, usually if you know two of them, you know also the third one. And this is an explanation, which is that actually there are more refined invariants of singularities. And those are not just numbers, but some sets of roots of unity or sets of rational numbers. So one such a set is the eigenvalues of monodromy, as I already mentioned. So this gives us a set of roots of unity because all the eigenvalues of monodromy are roots of unity. This is another theorem of Milnor, I believe. So we can take these eigenvalues. And then there is a very deep and complicated invariant, which I will just like give a brief idea because it takes time to define it, and I just want you to have some like brief idea what is it. So we have this so-called spectrum. It is not really, so when somebody says spectrum, you would expect that this is like a spectrum of some operator, right? Like another eigenvalues. So not really. It is, I mean, the idea is that you start with the monodromy and you have roots of unity. So those are e to the 2 pi I times some rational number. So you want to extract this rational number out of e to the 2 pi I q. So you want to get q instead of e to the 2 pi I q. So the thing is that of course there is an ambiguity, right? You can take q or q plus 1, q plus 2. You can take any integer shift. But here we have, so on this Milnor fiber. So now we go beyond Milnor to Arnold and Steenbrink, so Russian and German school, and Varchenko. So these people figure it out that on this Milnor number, which is, so this is a smooth manifold, but it is still a complex surface. So you can try to find some Hodge structures. And so Hodge structure is basically some filtration on the cohomology, satisfying some properties. Hodge structure, you can find a Hodge structure on cohomology of every Keller or complex variety. But you can also find Hodge structures in this situation when the variety degenerates to a singular variety. And those are usually some more, or you can also find by theorem of Deligne, you can find actually you can find Hodge structure on any variety which doesn't have to be closed. It doesn't even have to be smooth, but you need to take more general theory of mixed Hodge structures. So mixed Hodge structure has two filtrations. So one is this usual Hodge filtration. The other one is weight filtration. So it kind of mixes Hodge structures which live on the first, second, third cohomology together. So it mixes various degrees of cohomology, or these Hodge structures which live on the various degrees. Yeah, so it's like if you remove a hypersurface or point from a curve, you kind of want to still remember something about the Hodge theory of the point. So this is why you have like various degrees. So there is a theorem of Steenbrink and Varchenko, which says that you can find a mixed Hodge structure on the Milnor fiber MT. And so now you can combine it with the monodromy. So you have a vector space, which is your cohomology. It is filtered by Hodge filtration. You forget about the weight filtration for now, and you also have eigen decomposition by the monodromy operator. So you combine those two operations, and the monodromy tells you which root of unity you take, and the filtration tells you which logarithm you take. So, for example, for surfaces, there are three pieces in the Hodge filtration. So you can see it on this diagram. So the numbers, the rational numbers which we consider are from -1 to 2. So we take just interval of length 3, and for each of these eigenvalue of monodromy, we find a preimage which can lie in one of these three intervals. And it is exactly this Hodge filtration information which tells us in which interval we take the preimage, the logarithm. So this is the idea of the spectrum. So it really uses heavy analytic or algebraic machinery of mixed Hodge structures. Stibring constructed this mixed Hodge structure by considering this resolution. So there is not much. This is not very topological. This is really algebraic or analytic. So here is an example. So there is a mistake here. There is a typo. This E8 singularity is a. So are there any questions about this? Okay, so hopefully you got some rough idea how to construct some very cool invariants of singularity. So here is an example. So we take x squared plus y cubed plus z 5, z to the 5. So this is a hypersurface which has some horrible singularity at 0.000 because all the derivatives are 0. So the Milnor number is 8. This means that if you deform your hypersurface to a smooth one, the cohomology has rank 8. And actually, this is this very famous E8 lattice. So the signature of this cohomology is 8. This is why we call this singularity E8, because it is those like the simplest singularities are labeled by ADE Dynkin diagrams, which also correspond to these lattices. And geometric genus is 0 in this case. So if you take the resolution, the first cohomology, you will get 0. So and now the spectrum. So there are 8 eigenvalues because the full rank is 8, and it's the monodromy can be diagonalized, and the eigenvalues are like this. So you see that there is a nice so this is not a this is now the spectrum. So we see that there are no numbers in the interval -1 and 0, and no numbers in the interval 1 and 2. So this means that this Hodge theory is kind of funny in this case. Yeah. So the only thing which matters is this middle interval, and we have nice 8 numbers. You can notice more things. For example, you can notice that this is symmetric by the origin 0.5. So this is again something deep, and it has something to do with this symmetry of Hodge theory, as in cohomology you have like like HP0 and HP. There is this like left and right symmetry. Sorry, H0 and H. I'm sorry. Like you have H00, H10, H11. Sorry. Once again, if you take, for example, the first cohomology, or you have H10, H01, and you know that H01 is the same as H10. Yeah. So that's what I wanted to say. Yeah, and there is another reason why spectrum is really, really interesting and important. And this is not just the symmetry, but it tells us how the singularities change. When we deform one to another. So for example, you can take E8 singularity, and you can add some term here to the equation, like of such that in the end you degenerate to a simpler singularity, which is E7. So you can think about it as some kind of morphification. So you have a complicated singularity at 0, and then you deform the polynomial, so you split it into two simpler or one simpler singularity. For example, if you take function x cubed and you add plus lambda x squared, you will see that your usual function x cubed, which has an ugly point at 0, it splits into two usual nice quadratic critical points. So if you deform E8 to E7, then the spectrum behaves very nicely, and it behaves semi-continuously in a sense, which means that you may notice that now we have 7 dots, and so the thing is that there are less of them. So this is one way of semi-continuity, that the number always goes down, but there is more. For example, so the theorem states that if you take any interval of length 1, like from minus 0.5 to 0.5, then the number of the spectrum of the elements of the spectrum of E8 is always greater or equal the number of elements of E7. So this holds for any open, so any interval which is closed on one side, and in some cases it also works for closed intervals. So in this case it works for all intervals of length 1. So this gives you many applications in singularity theory, because this is in general very, very widely open problem, how to find which singularities can degenerate to other singularities. And this gives you one condition when this is not possible, and very, very strong condition. Yeah. The spectrum is not like the strongest invariant. You can still get something. I mean, you can have singularities which have the same spectrum, but it is a pretty strong invariant. Okay, so now I want to go back kind of to the topology. So because this talk should be about the interplay of topology and geometry, so I want to compare curves and surfaces. So curve, we saw one curve, and we saw that it gives us the link. There is this unfortunate thing that link of a singularity this is the same word as a link as a bunch of nodes in S3. So there are two meanings, but so link of a curve singularity is just a node or the link in the usual sense in S3. And what really matters when you have a link or not is the embedding into S3, because otherwise, if you don't embed it into S3, it's just a bunch of circles. So you have no invariance except a number of components. And we have this, so on the analytic side, we have this monodromy matrix. And this has an analog on the topology side, which is Alexander polynomial, because this is Alexander polynomial of a node is actually exactly the characteristic polynomial of this matrix. So the roots of Alexander polynomials are roots of the eigenvalues of the monodromy. And there is a very nice and much more recent story which tries to generalize kind of this relation to the Homefly polynomial. And this was a conjecture of Shende and Oblomkov, and proved by Maulik in 2010 and something, that you can actually also get Homefly polynomial, which is a big generalization of Alexander, by computing some Euler characteristics of parts of Hilbert scheme. So this is now Hilbert scheme is like a some moduli space of ideals supported in this singular point. So this is very analytic, very algebraic. So there is this very interesting relation, and there are also conjectures because you can categorize Humphrey polynomial to this Humphrey cohomology theory, and so this is supposedly related to the cohomology of Hilbert scheme, but this was not proved even for a torus knot. So even for the simplest case, this is not proved. And there is a lot of like ongoing research in this area, and also there is a lot of I mean, many people would like to know what is an analog in higher dimensions. So this nobody knows as far as I know, and this is kind of what everybody tries to do, including us. So now I will say something about the surface singularities. So now this is very different because the link now is a 3-manifold embedded in S5. But here we can, so 3-manifold, now it's not in general, it's not a 3-sphere. It's a 3-sphere only when you take the simplest singularity, so A1 singularity. So what actually matters is the topology of this 3-manifold. And it is not really clear how to use this embedding into S5. So of course, when I first saw it, I was like, I thought like we should use this embedding, right? This is the important thing because this is what we have in the curve singularity. But the problem is that there is no clear way how to define Alexander polynomial in this case. There were papers of Borogic, Nemeti, and somebody, Livingstone, which generalize this slightly, and then they try to do this for surfaces too. But this paper has been published like 10 years ago, and there is an error in it. So they found like easy counterexamples for their claims. So there is no way how to define Alexander polynomial. I asked Borogic, and he says that they know how to do it, but they are stuck on another project. So maybe in 2 years they will publish the paper. So who knows? Yeah, but so this is another interesting thing, but nobody really knows how to use this embedding into S5. So what we do, we avoid it. We don't think about this embedding, and we just concentrate on this 3-manifold, which still gives us quite a lot of information. Of course, we cannot recover the geometry, but we can still get something. So this also started by Milnor, who proved this thing that S3 is the link if and only if we have A1 singularity. And now it continues with many papers of Val and Nemeti and others. I mean, many people, but mostly around Nemeti, and they Nicolaescu also. So Nemeti and Nicolaescu have many papers on the relation of geometric genus. So this is an invariant of the singularity given by analytic methods. And so first of all, there was this relation to Casson invariant, this famous Casson invariant in a 3-dimensional topology. But this worked only for the simplest singularities. So for example, it works for these singularities E8, but it doesn't work for much more general singularities. But they find out a better version, so they related to the Seiberg-Witten invariants of 3 manifolds. Those are some invariants which are assigned to spin C structures on 3 manifolds, and then they then always generalize it. Then they find counterexample for the more general version, and so they improve this theorem all the time. And there is a nice talk of Nemeti in the International Mathematical Congress in 2018 about these stories. So if you are interested, you can see this talk. So I wanted to emphasize that this is really different. Now I just want to check the time. Okay, so now I want to talk about this Poincare sphere more precisely. So this is just a funny picture that if you want to think about Poincare sphere in some like nice way, you can take the solid dodecahedron and you can glue the faces by rotation of 1/5 of the full angle, and this is the Poincare sphere. So if you are a topologist, you can try to imagine in this way. But for us, it is just the length of the singularity. Again, there should be Z5 here. So something about the Poincare sphere, because this is kind of the model example of what's going on next. So it's a closed smooth three-manifold, and it is a homology sphere. So this was the invention of Poincare, that if you compute the homology of this three-manifold, it is just the homology of three-sphere. So the question was, is it also three-sphere or not? Yeah, but it's not, because if you take the first fundamental group, which you can probably see somehow from this picture, or you can use Van Kampen theorem, you will get 120 elements. Another nice property is that it is actually the boundary, as we know, it is a boundary of this Milnor fiber, which is a four-manifold with intersection form of E8. So E8 occurs here again. Yeah, and so now I want to get to some more modern story. So this is this. So I will talk about Witten, Reshetikin, Turayev invariants, and then Gukov, Putrov, Pei, Vafa invariants, and so-called modularity. So we have some basic invariants as P1, but those are usually just some numbers or groups or something very, very discrete, and we want to find some analytic invariants, some nice functions. So that's why we want to explore the modularity properties of three-manifold invariants. So this is an invention of Lorentz and Zagier, that you can actually get some modular forms, so some special functions out of three manifolds. So let's start with the Poincare sphere. We have some, so we have quantum invariants. So first of all, we have Chern-Simons of the connections on the, so we can take SU2 bundles, and we can take connections and compute their Chern-Simons action. And then there is this more refined story of Witten, Reshetikin, Turayev. So Witten wrote this famous path integral for Chern-Simons theory, and then Witten and Reshetikin and Turayev found a version, like a mathematically well-defined version using the surgery of the three-manifold. So they constructed some invariants labeled by an integer n, and like this level of the Chern-Simons theory. And what Lorentz and Zagier did, they considered these two functions. So just let's take a quick look on these functions. So we take some Q series, so power series in variable Q, which has some rational power in the beginning, and then only integer powers and integer coefficients. And so they considered these two functions. Somehow they found it. Actually, only the first one is relevant for the WRT invariant. So WRT invariant were already defined. They were ways how to compute them, and they noticed that if you take this series theta plus, and you take limits to, so this is a nice holomorphic function in a unit disk. I mean, except this funny power, but this is very nice. So you can take radial limits to roots of unity, and if you do it, so you have roots of unity e to the 2 pi I n for all n, you will recover this Witten, Reshetikin, Turayev numbers of the three manifold. So this is kind of a nice way how to write all the Witten, Reshetikin, Turayev invariants at the same time, and you have much more, because you have a nice function which is defined everywhere in the open unit circle. And this is the first observation. And the second observation is that if you add this function theta minus, then those two functions together as a vector, they have very nice modularity properties. So they form a vector valued modular form for the full SL2Z group. Actually, those are kind of those are yeah, okay, I'll talk about this later. So they form some nice modular forms. So it means that if you change tau, so tau is this logarithm of q, if you change it to -1 over tau, then this will just multiply by some matrix, which I will show in a minute. So and now, so what is like my observation, and it is very stupid, but somehow it seems that people didn't pay much attention to this, or didn't realize it. So these numbers are related to Chern-Simons invariance. This was observed by many people, but these numbers there is not so clear meaning of them. And now if you take a look on the spectrum of E8, which I showed you on this picture before, we have these 8 numbers: 1, 11, 19, 29, and 7, 13, 17, 20, 23. They are all divided by 30, so they're all in the interval 0 and 1. And so these numbers they appear here in the expansion. So it is good that Zagier always puts some piece of the expansion, like the explicit expansion in his papers, because I could see these numbers and I knew the spectrum of E8. So, and the number 30 is also here because when we generalize these formulas, we always have this 4 times this number. 4 times some number, and the number fits this denominator of the spectrum. So this gives some, like hint that maybe these things could be related. Yeah, and so this is what we try to investigate now. So maybe I will. I have like 15 minutes, right? Yeah. Are there any questions?
So just a stupid question, this M, that is your Poincare sphere, the thing you calculate the ratcheting into Rife invariant of?
Yeah. So yeah,
okay.
I take this function and I take radial limits, or Zagier and Lawrence take the radial limits, and they compute a Witten ratcheting into Rife of this closed 3-manifold of the Poincare sphere. Yeah. Yeah. So that's why I was looking at the E8 spectrum, because this is E8 singularity. So yeah, so so I mentioned these theta functions. So these theta functions are generally written in this way. So we take q to the some quadratic term and we multiply it by L. So they are these 3.5 unary theta functions. So if you take so basically the data is the integer m, which is 30 here, and then you take all the residue classes modulo m. Actually modulo 2m, so there's 60 of them, and if you take them together, you will get a vector of 60 like components, and this gives you a vector valued modular form, which is called vector Weyl representation of double cover of SL2Z, double cover because of this half here. And yeah, sorry, and I was lying slightly, sorry. So this is not true. So the true is that you first need to take this Eichler integral of this theta function. So Eichler integral is that you take here, instead of L, you take the sine of L. So you kind of destroy this theta function in a sense, because it will not have this modularity property anymore, because you put some funny signs here, but it still has some weaker property, which Zagier calls like a false theta function, or quantum modular. So this is called false theta function or Eichler integral, but it fits into this framework of quantum modular forms. So you need to take this Eichler integral of this, and then you recover Witten ratcheting into Rife. So it's not just limits of this theta function. This would be too simple, but you need to take this this modification, but very simple modification. Basically, this is just some derivative of theta function with respect to second variable, which I don't write here. Yeah. So in this Poincare sphere again, so just briefly, so we have this we can write this theta plus as this combination. We have these numbers here from the spectrum, and the matrices are written here. So we have two very explicit matrices, which gives us the behavior of these theta functions. There should be minus here when we do the modularity transformation. Okay, so now the question is, can we? So there are many questions. So one question is, can we generalize this to other three manifolds? So there has been a lot of work on generalizing Witten-Reshetikhin-Turaev, and also a lot of Witten-Reshetikhin-Turaev is, of course, it's completely general. It works for any three manifolds. But there was a question how much you can generalize this Q series, which gives you Witten-Reshetikhin-Turaev as a limit. And this was done by Waffa and Gukov and Pei and Putrov in this paper. It started with observation of Waffa in 90s that you can get Witten-Reshetikhin-Turaev as radial limits of Eichler integral of some characters of vertex operator algebra. So basically, this is somehow like some vertex operator algebra character, and so they then they related it to these vertex operators algebras, and they were able to construct explicitly some invariants which they call ZB hat. And this B denotes dependence on a spin C structure on the three manifold. So it is more refined because there is no spin C structure in Witten-Reshetikhin-Turaev. So in this E8 case, there is just one spin C structure because E8, this manifold, as I mentioned, is a homology sphere. So spin C structures are in a non-canonical bijection with the H1 in the first homology group of the manifold. So here the first homology is 0. So it means that there is just one spin C structure, or so there is just one ZB, and it is this Eichler integral of this theta function. But in general, if you take E7, for example, so E7 has two spin C structures, so you will get two invariants, and you need to take some linear combination of them to recover Witten-Reshetikhin-Turaev. And this is now like a big business here, that everybody is computing these ZB invariants for more and more general invariants. I mean, there is no general definition for general three manifolds as for Witten-Reshetikhin-Turaev, but people are trying to make more and more general versions and try to basically recover all invariants using these ZB hats. So this is one way. So this is one question which is now very well studied: how to find these Q series which recover Witten-Reshetikhin-Turaev. And then there is this question which is I think in a sense much more tricky, and this is the question if we can find another function, or if we can find a vector valued modular form such that these ZBs, these invariants are components of this modular form. So basically, in Lorentz and Zagier, they were really like optimistic that you can do this for any three manifolds, and they now have so Zagier has very recent paper with Garoufalidis doing this for hyperbolic three manifolds, I mean, personally, I'm not so optimistic as they are, or at least I don't think that this has been really like. I mean, this has been studied, and it has been studied in a paper of Cheng, Chun, Ferrari, Gukov, and Harrison, 3D modularity. So in this paper, they try to generalize. So they try to find these modular forms for other three manifolds, so this works very nice for manifolds which looks like this x cubed plus y4 z5. So they are of this. So the singularities are of this diagonal form. So so there are no mixed terms, and these three numbers are co-prime. Then you have just one spin C structures, just one Z0, Z hat, which you label by 0 because there is just a trivial structure, and you can find some. So this is the Eichler integral. This corresponds to this Z hat invariant, and you can find five more data functions, such that together you will find, or combinations of data functions, such that together you will find a modular form. This is very nice and very interesting because this is related to many other things. For example, you can not just recover the Chern-Simons invariants, but you can even kind of recover the these rows of this model vector modular forms. They're actually in bijection with non-abelian connections on these three manifolds, so non-abelian SL2C connections. So even though that we start with some manifold with some invariants which are kind of depending only on the abelian connections on the spin C structures, then we recover somehow kind of the full data of all SL2C connections, and you can see which of them are real, which of them are can be conjugated to SL2R, etc. So, but then then in this paper they consider more general manifolds, and they have table of 36 examples, and I tried them, and I found some errors there. So they are now trying to repair it, but my feeling is that this really is more deeper and more complicated. Maybe not so much, but definitely their formulas need some improvement, and it is a question how general can this be. So this has something to do with the story I described in the beginning. So this story of Nemeti and Seiberg-Witten invariants. So this works for some singularities, but not for all of them. And this story about so I should, okay, maybe I have like 4 minutes. Okay, so I should maybe say the main point. So the main point is that we found that this relation of spectrum and these modular form, so we really need full modular form, all the components, works for all Brieskorn spheres, so all links of singularities of form x to the a plus y to the b plus z to the c, where a, b, c are coprime. And moreover, we found that this also works for all ADE singularities. So for example, for E7, but then we don't take the spectrum of E7, but we rather take the spectrum of the so-called universal abelian cover of the singularity. So here is the example. So we take E6, this is x squared plus yq plus z4, and we can compute the theta functions in the representation or in the modular form, which we get from these z hat invariants. And then we see that there is this 1, 5, and 2 times 3. There is this multiplicity 2. And this really corresponds to the spectrum of a different singularity. So it's not this E6, it's D4. So this is a singularity which covers this E6. And it is maximal such that the covering group is abelian. So the covering group is actually this H1. So it's actually this number of this Z hat invariants. And these abelian covers, they really appear everywhere in this story of Nemeti and Seiberg-Witten invariants. So maybe I should like just now say some conclusion. So so it seems that there are some modular forms, but it is not clear how to get them, and it seems that they might be related to the spectrum, or if not to the spectrum, this can be thought as some kind of lift of this relation of Seiberg-Witten invariant and geometry genus, because geometric genus has a refinement, the monodromy or the spectrum, and the Seiberg-Witten invariants are related to Chern-Simons invariants, and they have this refinement in these theta functions. So it is possible that there is some relation, and it is not clear how far we can get in the generality. And so in the future, we would like to generalize this for other surface singularities. We would like to relate it to this work of Nemeti and Seiberg-Witten, and also so this is kind of about relation of 3 manifolds and 4 manifolds. And this is actually how Waffa and Gukov originally find out these invariants of 3 manifolds. They started with 4 manifolds, and they were doing some of these Waffa-Witten invariants. And Waffa invariants, they are related to Seiberg-Witten invariants. So we hope that there could be some like big square of like Waffa-Witten invariants, these Z-hat invariants, Seiberg-Witten invariants, and these invariants of the singularity, so geometric genus or spectrum. And this should be all somehow interrelated, and it could explain this modularity of these invariants. So this is. So the question is like, so far we have some numerical relations, and the question is if there is some like really conceptual explanation. Okay, so here are the references, and it's time to stop.
Thank you very much.
Are there any questions?
Yeah, I'm there.
Janči, you're asking?
Yeah, I have a question.
You're muted.
I have a few questions.
Yeah.
One of them is when you showed this series.
This one.
And the yes, this one, and the eigen, like this spectrum. So these are like, yeah, these are the eigenvalues of the monodromy matrix.
There are logarithms of them. If you
okay.
if you
yeah, okay, of course.
If you take e to the 2 pi I of these rational numbers, you will get the eigenvalues of them.
But in those these Eichler integrals, there is more terms. So do you have some mechanism why they drop?
Yeah, there is like, of course, there is like infinitely many terms. But if you write it as this like if you write it in this form of these Eichler integrals, you just have like few residue classes, right? Because it kind of repeats. Yeah, so this is some theta series, and you see that it is like a sum over infinite sum or over some residue classes. So what I'm only saying is that this spectrum should be related to these residue classes, or like the question is like which residue classes you want to take, because it's kind of clear that you want to take some theta functions to get Witten-Reshetikhin to arrive, but you don't know which residue classes. So okay. Yeah, but yeah, you're right. I don't know. I don't really say anything about like these theta functions as a whole. So this is
okay.
This might be related to this sheaf counting. So we would so spectrum is really just like taking some dump numerical invariant. I mean, it's very good, but it's still just a numerical invariant. But you could consider like in this story of Homefly and Hilbert scheme, you are really counting some sheaves. You are doing some like so this is how you recover like really like an infinite series. So what you actually recover is like an infinite series, but this can be, you have, when you multiply an infinite series by another polynomial, you can get just a polynomial. So if we want to find the analog, we should do this Waffa-Witten or try to do some counting of sheaves to recover kind of every term.
Okay, and like this Reshetikhin Turaev, you described this is for Chern-Simons with the structure group being SL2.
Yes.
Right?
Yeah.
And but you get a Chern-Simons for any, let's say, simple
Yeah, that's
Lie
true.
group.
That's true. And actually, well, like 2 weeks ago, we talked about this with Gukov, and he was like immediately skeptical because he was saying like, oh, there is this SL2C group or SU2 group, and you have no group here. But then he like I sent him these papers about like relation to Cybergwitten, you know, this geometry genus and Cybergwitten, and there is this thing that Cybergwitten is kind of related to Donaldson invariants, right, which are for like SU2. If I mean, I don't know these things much very well, but then there is this like thing that if you take SU3 or SU4, it should be still related to Cybergwitten invariants, but in some more complicated way. So so maybe it is because actually Cybergwitten is like more natural in this to think about in this story, and it is very easily related to SU2, or like this is the easiest way, and not so much to other groups. But you're right, you can consider this for any groups, and but like even computing the Casson invariant for other groups is not easy. So yeah, so this would be much harder, and I don't know how to. But yeah, I mean, for me personally, I don't understand how like this SU2 appears in say monodromy. Yeah.
Okay, so, but your guess would be that the bigger groups they would contain, or like the WRT for bigger groups would contain like finer invariants than just the monodromy. Or is rather is the group related to the specific singularity, and you should find different groups for different singularities?
So what Nemeti says in his talk in 2018, he calls this relation of Cybergwitten with monodromy or like or singularities. He calls it like I mean, it's a theorem for many singularities, but he still calls it like that it's a possible coincidence. You know, so even in this case, it's still kind of unclear. So I cannot really say if you get, so the problem is that in general, like, you know, you lose a lot of information when you go from this single. You cannot in general recover spectrum from the link. This is like a this you cannot do. So also we in the end we get like a spectrum of a different singularity, which is kind of easier in a sense, this Abelian cover. So yeah, I mean, this is I would say that my answer is that I cannot say anything about other groups.
Okay, it was still very interesting. Thank you very much.
Okay. Any other questions?
Here in Prague, we don't have questions.
Okay.
So,
yeah, so then, thank you.
Yes, thank you so much for the
attention.
extremely cool research.
Yeah, maybe I just should say that. So it's kind of bad that I didn't like mention any physics here. So I'm trying to learn it, and then maybe eventually. But these invariants, these z-hat invariants, they have like so the motivation comes somewhere from M theory, and M theory gives you this like 6D superconformal theory on a 5 brane, and then you have 6D theory, so you can compactify it on a 3 manifold, and this gives you a three-dimensional theory. So if you take partition functions for these 3D theories, you can get these invariants. So there is a lot of like physics hidden in these stories. Yeah. So maybe next time once I will learn it. Yeah.
Yes.
Okay.
Okay, so thank you so much again. Another round of applause. Yeah, so